Okay. Okay, this is the last year final exam. Okay, so I hope you already tried to practice with the question that I gave in Google Classroom. So you can check Google Classroom and download the last year final exam. We will start to solve some question from here. Um, Probably we will have maybe 4 or 5 or even 6 questions. So let's start from. I think we can start from number. I think number two, number three, four, number three, four, or maybe number five. I think we can start with. I think number one is not too difficult. Number. I think we can start from number two. Let me go here. Okay. Okay, so we start from number two, evaluate the definite integral integrations from 0 to 1, x with power of 5, multiply with e with power of negative x cubed. Okay, you can try to solve first. Okay, I give you maybe a few minutes, 2 3 minutes to solve this. Okay, I think I'll try to solve it for you. All right. Now we start with the. Uh, let me write the integrations. Okay. If you look the form, okay, the form of integral, it start with the x to the power of 5 and e. Okay. Uh, we know that e will, if you integrate or differentiate, it will stay similar with e, but it has this power of negative x cubed, which means when you integrate, for example, with power 2x like that, still you have e 2x, but you need to multiply it with 2. You have the general if you want to differentiate. Same thing with the integrate. So this is if you differentiate, if you integrate, this will be still the same, but you have divided by 2 like that. Okay, if you integrate. Okay, now if we have this cube, okay, and we have x5, I mentioned in the early class, okay, when you have e and you have the other one is like power functions or uh, power form like x5, x2, x3, it's better to think this as the one that we need to derive, and this is the one that we need to integrate. But okay, if you look here, we have x with power of 5, right? Then we may have, if you have, we will have really, really long, at least quite long, uh, how many times we derive, it's still, I consider a very long process, right? So a good way to see this form is we can look at this, okay, this negative x cubed, and then we have this, okay, x cubed. If we want to derive this become 3x squared, right? Okay, and if we use this as u, if this is u, then this will be 3x squared dx du, right? Okay, let's change this. Okay, let's change this. And still the endpoint is still the same because it's just 0 and 1. X cubed is still the same, right? So we have x5 e negative u, and the x will be become, this is 3x squared. This is du. Okay, let's solve this. This is cancelled, and this will be 3. X with power of 3 is 2, right? Okay, so let me write this is 1 over 3 u e negative u du. Okay, now I think this will be relatively easier to be integrated by parts, right? Okay, so we can integrate by parts. and carefully plug in the 1 and 0. Okay, that's the answer. This will be D. Okay. Um, yeah, this is the process. Okay, if you look back at the questions, you can directly use the integration by parts. Okay, if you're looking this X5 and E. But as I said before, uh, when you do that, you have several integration by parts. I think you need to have 6 times because you have x with power of 5. Right? We need to derive at least derive 5, 6 times, and it will be a very very long integration by parts. And I don't really think that the time will be enough if you try doing that. But instead, you can have substitutions, and then the second part will be using integration by parts. I think that will be easier in this case. Okay. Okay. Then we can go to the next question. The next questions will be okay, I think number 3, okay, probably number 3. Try to look at the question and imagine, or maybe you can solve it. Okay, this is if you want to solve uh, this one, the idea is simple, um, but what you need to be careful is the curve. Okay, if you look at the curve, you may think that like probably we need to factorize if you can factorize. Okay, so let's factors. Okay, that will be the curve. So the curve will have the asymptote, right? If you want to draw the curve, I don't think you need to draw all the curve because you only need to draw from 0 to 1. So probably this will be uh, half like that and half one. So probably this will be maybe this is a little bit down, maybe getting around there. Yeah, it's really small. I believe that it will be the curve, a part of the curve. Okay, that's the only curve that we are concerned. Okay, because the other part, like in x equal -1, maybe here, and x is -2, maybe here. This is the asymptotes, and it's too far from what we have in the questions, right? We only care about this part here, these two parts. So we need to find the volume if we rotate this. Okay. So will be the volume. Okay. I believe it's much more simple if we are just using the x like that and then we rotate. So the integrations, let me just write integrations first. Integrations from 0 to 1. Okay. We are just using the disk formula. Okay. It will be pi, then 1 over, or let me use the bracket, 1 over this one, x plus 1, x plus 2, and this will be squared, and then the x. Okay. Now this is the first part. Okay, the first part to identify first the functions and how to solve the volume. Okay, that's the first part. The second part is to integrate. Okay. Okay, since this is having quite big fractions in the denominator, what we can do is we can consider functions g. This is having x plus 1 squared, x plus 2 squared, because we have squared, right? So we will have a partial fractions. This is x plus 1. This is uh, x plus 1 squared. Okay. So we'll have 4 components, and we have a constant here, constants there, constants. Okay, as usual, we need to solve it to find A, B, C, D first. Okay. So A is a little bit long to solve, but let's just write down all the process here. Okay, and this is equal 1, right? Okay, now we can set, let me write in another color. Set x is -1 and x is -2. Okay, why? Because when x is -1, some of them will be becoming 0. Okay. So when we set x equal -1, this will be 0, this is 0, and this is 0. So we will have, uh, this is -1, -1 plus 2, it's 1, so squared, so b will be equal 1. Okay, and if you set x -2, it's 0, this is 0, this is 0. Okay, and we will have d is equal, -1 squared, d is also 1. Okay, and we need to find a and c. Okay, we can find a and c through we solve this first. Okay, so we solve first. Okay, we solve first. uh, a x plus 1, this will be x plus 2 squared, this will be x plus 1 squared. So I plug in b and d equal 1. Okay, we can factorize x plus 2 squared. This is a x plus 1 plus 1, and then plus x plus 1 squared. I factorize this second time. Okay, let me just finish this. This will be ax plus a plus 1. This will be x squared plus 2x plus 4. Where we can multiply. So this will be ax cubed plus 4 ax squared plus 4ax plus ax squared plus 4ax plus 4a. And then this part will be x squared plus 2x plus 1. This is cx plus 2c plus 1. We multiply same here. This will be cx cubed plus 2 cx squared plus cx plus 2cx squared plus 2cx plus 2c plus x squared plus 2x plus 1. Okay. What we have here is we need to solve this and look at the, we can choose, okay, we can choose, we have x cubed, so we can consider, actually you don't need to multiply all like I did. Okay, you can just end somewhere, okay, from a and c. And you can just think that there will be no other x cubed, right? So we can simply say that a plus c is 0, okay? And also the other one, uh, we can see the other one. Then we can see this for a. Uh, so we can see the x, okay, x. I think we can. I think the. Wait, I think for a and I think I think for a x squared. So for a, 5a, right? We have 5a, 5a for the a. I think I haven't finished this. This should be having another one plus x squared plus 2x plus 4, but doesn't mind. Okay, 5a. Let me check 5. 4a. Okay. Okay, 5a plus 1, right? 5a plus 1. And then the c will be 4 cx squared plus x squared. So this will be 4c plus 1. This is also 0. Okay, let me check one more time. 4. For ax squared. Okay. Okay, I think we can solve this. 2a plus 2c. Uh, 4a plus 4c. This is, we have a is -2. Okay. And we can solve the other one as well. Negative c is -2. So c is 2. Okay. So we get a is -2, c is 2. Okay. Okay, just careful on finding the variables. Okay. So we can have, let me write here, a is -2, b, or we can write in the equation. So this will be equal with -2 x plus 1 plus 1 x plus 1 squared plus c is 2 x plus 2 and d will be 1. Okay. Now we can now solve this in our integral. Okay. Let me write in the next page. Okay, so it take too long. So integral from 0 to 1, let me write the equations. This will be equal with integral -2 x plus 1 x plus 1 x plus 1 squared dx, and then plus 2 x plus 2, and then plus 1 x plus 2 squared dx. Okay, I think we can solve this. Okay. Oh, I forgot the pi. So volume, this is pi. Let me move a little bit. This is pi. And this will be -2 ln x plus 1. Okay. This is another ln. Let me write here. Plus 2. And also ln x plus 2. And this one will be -1 over x, right? So we can write this -1 over x plus 1 and -1 over x plus 2. Okay, for this part. And then the whole thing is in input 0 and 1. I will give you tips. Okay, when you have ln and ln like this, you have a negative, you can put the negative here. Then you can write down, this will be 2 ln, and this will be 1 over x plus 1. Right? And this is, you can combine, and you can write 2 ln x plus 2 x plus 1 like that. Okay, just tips that when you have an ln, and you can simplify. And we put 0 and 1. We put 1, so this will be ln 3 over 2 minus, we put 0, this will be 2 ln 2 minus 1 minus half. This will be 2 ln 3 over 2 divided by 2 because of this minus, okay? And plus, we evaluate this and evaluate this. This will be 2 over 3, okay? Still we need to solve. We can put 2 over here. So this will be pi ln 3 over 4 squared, okay? Sorry, this is so this will be 2 over 3 plus ln 9 over 16. I think this will be A. The answer is A. Okay. 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 So I think the time will be the difficult part on this is the partial fractions. Okay, the partial fractions. And since it's not really a huge point, this number, if you think you need to skip this, I think that you can skip, okay? Because it's only 4 point, this part. Okay. We can move to other question. Let me just go to number 4, and then we can go to the other part. Okay, this is just the part A. Later, I will share you the notes that we have today. Okay, later. Okay, number 4 is quite simple, and I need to review this to make sure that you understand about the surface area. Okay, so okay, imagine this is the x cube. X cube, let's say that is our x cube, and we are going to evaluate from 0 to 2. Say here, and you need to rotate through x-axis. Okay. So the important thing on the surface area is the first is we need to identify the radius, right? The radius of this the solids. Right? The radius is here, which means we can use this is y, right? So if we are going to evaluate the formula 2 pi y dx, let's just start with this. Okay, this is the arc length. Okay, and the nice thing on the surface area, when you need the arc length to be using the let's say the arc length is 1 plus, and then this is dy over dx. So you have dx here, then you can just use dx. Okay, so this will be a dx, and then dy will be x cubed, right? And all things here will be nicely in x form. Okay. Same thing when you try to rotate with the let's say the y-axis. Okay. Your radius will be this one, right? This will be your radius. This will be x. And the nice thing here, if you are looking for the rotation on y-axis, then this will be 2 pi x, and the ds is still ds. And since it's already x, and it's already, we know that this, we can have this in our arc length, so we can just use the arc length and taking it to the x, and we can solve this, right? So next thing on surface area is, you don't need to worry about the arc length, as long as uh, all the um, all the information are true. You can do whatever you want, and it depends on the form of arc length you want. Okay, and I think we can uh, set the arc length to be using dx. Okay, I think we can, let's start from here, from the dy over dx. So dy over dx is 3x squared. So our arc length will be, let me just write into the equation here. And this is still 0, 1, because that's the 0 or 0, 2, the interval. This is x cubed, 1 plus 3x squared squared dx. And we can directly get, if we need to just to find this, right? And the answer is B. Okay, it's not too long in the process. So you can actually, if you have this kind of questions, you can try this at the beginning, because you can do it faster. Okay. Let's see the other questions, which part that we are going to have. I think this one already in the class. I think we can. This is also in class. I think maybe number 9. But let me check if it is too long. Maybe we can have just half. Okay, I think we can try number 9. Number 9 is part B. Part B in our case here is, you can have multiple correct answers. Okay, multiple correct answers. So which means each number you can have, like, not only one correct answer, but multiple. For example, maybe the answer will be A and B, or A and C, or B, C, D, or all corrects. It can be happen. Okay, let's try number 9. Okay, let's try number 9. Okay, you can also try. You need to prove whether the statement's true or not. Okay. And for this one, you need to be careful. Okay, careful. You need to remember all the basics on limits. Okay, let me give you a few minutes to check this. Okay, I think we can check one by one from the uh, functions. So we have piecewise defined functions here. So first is we have when x is positive, and the second one is when x is 0 or less than 0 or negative. Okay? We can consider this with the limit. Okay? So we can check limit from the right and limit from the left. So first, we check point A. So limit as x approaching 0 of gx is equal 1. So how to check? So first, we can check the limit from the left or limit from the right. So from limit from the left is just 1, right? So we can write limit as x approaching from the left of gx. This is 1. That's true. But if we check limit from the right, we can check, and we can write as 1 equations like this, and then over x. Okay, this is 0 square root of x. Now, if we imagine 0 inside the x, we can check from here and check through this. This will be resulting 0 over 0, right? Because integral 0, 0 is 0. Okay? So we may apply L'Hopital rule. So we can use the fundamental theorem of calculus, and this will be resulting 1. This is x, get square root of x, and then plus. This is x with power of 1 over 4, because squared and then squared once more. And then plus 1. And don't forget to chain rule. don't forget the chain rule. Okay, the first part is not a problem, right? It's a converge one, converge to one. But the second part here is will be having divergent, right? That. So if you forget this chain rule, you may answer it's correct. But since this is diverge, then we can conclude that this is not equal with this, which is this becomes false statement. Okay, the second statement is going to infinite. Okay, as x going to infinite. Okay, we take the the positive one is gx. Let me write here. As x positive, gx will be 1 over x. Okay. Okay, now what can we do? What can we do now? Okay, the first thing we can do is we can consider, or let me write here, consider two integrations. The first is, of course, the question itself. The second one is this. Now, if you look this, okay, if you look this, and let's say we clear the integral, we can conclude that from the fractions, this will, at least this is true, right? At least this is true because of we have um, more additional components on the denominator, right? Okay, so we can check first. We can check first. This will result in tangent inverse, right? Tangent inverse d from 0 to square root of x. Okay, so this will be tangent inverse. At least this is tangent inverse square root of x, right? And if we have limit, then okay, if we have limit as x approaching infinity, then this tangent inverse, we can consider this as pi over 2, right? Okay. So at least the maximum limit that we can think from our case here is pi over 2. Okay, so if we have limit as x approaching infinity, can have this, let me write here, at least this is pi over 2, the maximum one that we can take, and this will be x. And since this is already a constant, then when we move the infinity inside, this will be resulting in 0, right? So I think this second one is a true statement. True statement. Okay. Okay, the third one, when you have limit as x approaching 1 of g prime x, this is, it says positive. Okay. Okay, when x is positive, okay, at x, we can write down the formulations. 1 over x. Okay. We evaluate the first derivative. We can do the product rule. And plus 1 over x. And then do the fundamental theorem of calculus, FDLC. This is x plus x 1 over 4 plus 1. And then when we limit this as x approaching 1 of g prime x, then this will be, let me just write first. Okay. Okay, let me make it into going up a little bit and a little bit resize. Okay. Okay, we can look here. Oh, wait, this is not 0, sorry. 1. If we check, this will be half, and this will be 1 over 3. So this part will be 1 over 6. Let me write 1 over 6 here, 1 over 6. And we check this going here. This is negative 1. and this will be 1, 0, 1. Let me write over here. So we will have 0, 1, or maybe I can write here first. Negative 1, or negative 0, 1, and then this. Okay, now look here. I don't think we need to write here. Write it like you. Okay, look from these integrations. So 4, 4, 0, t to 1. Okay. If we look at these equations, if we look at how um, the formulations, okay, this will result, a maximum will be limited in 1 over 3, right? At least this will be the limit of the or the maximum number that we can think from this fractions. Then these integrations will also at least the maximum that we can think is it will not be higher than 1 over 3, okay, from that logic. So if we assume that this is negative 1 over 3, we will have a negative 1 over 6, okay, which is not true, right? So this will be another false statement. Okay. Okay. Okay, let me make it a little bit smaller. Okay, the last statement. Okay, so we have x getting approaching 0, and we can look at left or right hand limit. Okay, from the left hand limit, we know that from the equations this is 0, true, right? The problem is when we have the right hand limit. When we have the gx, okay, we can first look on sine x over x, okay, and then we can have limit on the limit here. We can separate this, become And this is certainly become 0, right? This is 1, and this is 0. So this will be a 0. So the thing is limit from the left is 0, limit from the right is 0. So this is a true statement. The correct answer will be B and D. Okay, quite complex, but it is huge point if you solve this kind of questions. Okay, later I will give you the notes. Okay, so don't worry about all the notes from today's class. Okay, I think we can move to part C, and if we are still looking another question, we can look on the time we have. Okay, from here, I think maybe number 12. Okay, number 12 first. Okay, so we try first. Now let's check whether we can solve it or not. Okay, we can start with, if you look at the questions, okay, it says that what is the value of the f of 0, okay, which means we need to evaluate the functions at x equals 0. But okay, the function itself, it's satisfied for x not equal 0. Okay, so what we can do, okay, if this happens, is remember that we are having a concept of limit. Okay, we have the limit that is when x approaching 0 of f of x, then we can evaluate at least the limit for f of 0, right? Then we can look at the limit. Okay, I can write this x with power of -5 on the denominator, right? Okay, now first, if we evaluate the limit, okay, this will result 0 over 0, and we may apply the L'Hopital rule. So apply L'Hopital rule, that is, we can differentiate each component. This will be 5x with power of 4, and we can substitute to x with t, substitute x to t. So this will be 1 minus cosine x squared, like that. Okay, what's next? What's next? Okay, the next thing we can think, uh, we can look on the equation if you want. This is still, however, 0 over 0. We may L'Hopital again, but I will show you another way, uh, aside from the L'Hopital. Okay, let to make it easier, or I don't think we need to assume. I think we can directly see if we have cos to alpha, this will be resulting. Okay, and this so if we have cos, this is x squared, this will be resulting to sine squared, and this x squared over 2, right? Okay, okay, let's try to write that in our equations. So 1 minus 2 sine squared x squared over 2. Okay, now we have sine squared here, right? This will be cancelled, right? So this will be a positive. Let me write this as squared like that, and we have 2x with power 4. I can factorize 2 over 5 outside the limit, and this we can have x squared over 2 multiply sine x squared over 2, right? And this will be this one x squared, Let me move a little bit middle to the center, maybe here. Okay. Okay, remember that we have the property of limit that is sine x over x when limit of x approaching 0. This will be equal 1, right? So we will have now, looking at this x squared and this x squared, we may need to have, or we need to divide this by half, right? But we need to multiply with 4, okay? Okay, I think that is correct. So this will be perfectly 1 and 1, right? So we have 2 over 5 multiplied by 1 over 4, or this is 1 over 10. Okay, so instead using the L'Hopital that you may need to do several times from here, you can also think using the trigonometric property. Okay, so that's number 12. Okay, let's look again. What question do we have? Uh, yeah, hopefully we have time. Okay, hopefully we have time. Okay. Or do you have any requests? Which questions you need to answer from this last year final exam? If not, I'm planning to give you number 16 or number 11. Okay. Number 11 is which one? Okay, yeah, this is yeah, quite complex. Okay. So if you want this, so maybe we can have this as well. Okay. Actually, this is quite time consuming, this type of questions. Okay, so the first method, okay, the first method, we can check first from the limit or the Riemann formula, the sum formula. What we can do is we need to solve, or not solving, we need just to check. We need just to check whether all this is equals with the questions. So first, um, we can check when I is 0. This will result in 1 over 2n, and then this is e to the power of 4, and this will be 3. Okay. This will be e to the power of 4, 6n. And when I is n, this will be results in 4 plus 6, and this will be 3 plus 3. This will result in e with power of 10 and 12n. Okay. So basically, from what we have here, yeah, I think this should be uh, checking one by one. Okay, so this is start from using the delta x is 1 over 3 minus 0, or this is 3 over n, right? And then check when x is 0, e4 divided by 18 multiply with 3 over n. This is e4 and 6n. When x is 3, e10 and 36, and this will result in 12 and 12n. Okay, and this is equal, right? Equal with this, so this is true. And the second one is 0, 1, e4 plus x 6, right? And then 2, yes, this is b is correct. Okay, it's correct. And same thing, now it's 0 to 1, so delta x is 1 over n, right? And then same thing, we can check x equals 0, then this will be e4 6, right? Multiply with 1 over n, this is e4 6n. X equal 1, this is this should be here. This is e5, this is 8, and multiply with 1 over n. The first statement is true, the second one is wrong, so it's false. And then we look on C25, and this is start from here. We get that delta x is 5 minus 2 is 3, so 3 over n, right? And then we check x equal to E4. 3, 6 is 18. This will be results on E4 and 6n. Okay. And x5 is E10. And 36, 3 over n. So we can have E10 over 12n. And it's true. This is the same statement, so this is true. And number D is from 3 to 6, E. And we may know that this is from delta x is 6 minus 3 is 3, right? 3 over n. So we can check x equal 3 is E7. I think we can see that this is wrong, right? So let me just finish this. E13 and 12. Sorry, 36. So wrong answer here. So the true statement is A and C. So the answer is AC. Okay, this is came from the definite integral definitions. Okay, so I hope you get the idea from here. Okay, I think we can at least maybe the last questions. Okay, the last questions. The number 17. Number 17 is actually the bonus point. So it's having a huge point. So I hope you get the concept for number 11, this one, using the definite integral definitions, using the Riemann statement. Okay, Riemann statement. Okay. Okay, this one. Okay, the figure shows symmetrical with radius 1, horizontal diameter is PQ, tangent lines at P and Q. Okay, at what height above the diameter should the horizontal line be placed so as to minimize the shaded area? Okay, seems a bit complicated. Okay, so we have a tangent line. Okay, we have a tangent line at the P and Q. Okay, so this is a tangent line, right? This is the diameter, and this is the horizontal line. And this is the horizontal line. Okay, this is the horizontal line. Let me write here. horizontal line that the questions is asking. Okay, so we can move the horizontal line. Okay, and imagine that this will result in a variable of some variables. Okay, so we can change this height, like, let's say h like that. Okay, so first we can approach with a with a functions. Okay, and we need to design what functions we are going to use. For example, if we take, like, separate this by half like that, and making this as our y-axis. Okay, y-axis, and this is also this is the x-axis. Okay, from from there. Okay, and we can have a triangle inside. This is the intersections, right? So this is h. Okay, it says radius 1, so this is 1. Okay, so this is it. Let's say this is 0, 0. Okay, so radius is 1, and we may have the circle is x squared plus y squared equal 1. So this is also 1. Okay, this is 1. This is 1. So we can think the area between the curves. Okay, between the curves. Let's just minimize this part and the right part on the area, because the other one is the symmetrical. Okay. Well, let's minimize this. Okay. So first we need to find the area, right? Find the area. So we need to find the area either using dx or dy, depends on you. For my case, I will going to write in terms of x squared, 1 minus y squared. So x is square root of 1 minus y squared, like that. Okay. Why? Because if we are using dy, we get directly the height, right? If you look the h, okay, so this will be h, this will be 0. So we can compute 0, h, and 1 as our all three endpoints in our integrals, right? So first, integrate. So this is area of our function h. This is integrate from 0 to h. Okay, this one. Okay, this is the, let's say this is a1. Okay, this one is a2. So this is a1. Okay, a1. So 1 minus, oh, sorry, should be having 1. Okay, and dy, and plus from h to 1 of the 1 minus y squared dy. Okay. Okay, I hope you understand my approach here. This is my design functions, our model. Okay, you can have different kind of models as long as it is correct. Like, for example, you want to calculate from this point P to Q, that's also okay. But I would love to just this half part of the area because of the symmetrical. So It's the same thing. Okay? So we can just minimize the half part. Okay, so let's try to find the minimum area, which is we need to find this, right? If you remember, this is from optimizations. So we can compute the derivative. So the derivative will be solved by fundamental theorem of calculus, which is this is 1 minus y minus h squared, uh, 1 minus h squared. So we will have 1 minus 2, 1 minus h squared is equal 0. So to solve this, we can solve, and this is 1 over 2. So let's square both sides. So this will be 3 over 4. So h will be square root of this, or half square root of 3. Okay. Okay. That will be the number 17. I think number 17, the um, the difficult part is to understand the questions, I think, because it's combinations of area between curves and optimizations from the first or the chapter uh, 4, right? From the derivatives. Okay, and I think that will be the last question for today's class. Okay. Um, okay. I think I will just put in Google Classroom your quiz. Okay, chapter 6 quiz. I have graded your score. I will put into the Google Classroom. You can check later. Okay. After this class, I will upload. Okay, so that's it for our class today. This is the last class, okay, last course. So I hope everyone ready for the final exam this Friday.